by a logarithmic function. You see, quite frequently in mathematics, what one does is one deals with a particular special case in which one is interested. And having deduced very nice results, he looks at this thing and says, you know, all of these results came from a particular recipe, a particular structure that this system obeyed. What he then does is he takes this recipe or structure, gives it a general name, and now is able to extend this property to a larger class of objects. For example, let's look at it this way. What is the nice thing about logarithms in the traditional sense of the word? Remember when we learned logarithms in high school, by use of logarithms, we were able to replace multiplication problems by addition problems, etc. In other words, remember the key structural property was that the logarithm of a product was the sum of the logarithms. That was the structural thing that we used over and over and over again. In fact, it's rather interesting to point out that in many cases where we used the properties of logarithms, we never really had to know what a logarithm was. All we had to know was what? What properties did it obey, and did we have a book of tables so we could look up the logarithm when we had to? Well, at any rate, using this as motivation, we now define a logarithmic function. Specifically, a function f is called logarithmic if for all x1, x2 in the domain of f, f of the product of x1 and x2 is f of x1 plus f of x2. In other words, since we know what nice properties a logarithm has, let's define any function f to be logarithmic if f of a product is equal to the sum of the f's. Okay? Now you see, this may sound like a pretty simple statement, but it's quite demanding. In other words, notice, by the way, somebody says, I wonder if there are any logarithmic functions. You see, notice that by the way we began, there must be at least one logarithmic function, namely the usual logarithm. In other words, we know there's at least one function which has these properties. So the set of all logarithmic functions is certainly not the empty set. At any rate, let's see what we can deduce about any logarithmic function. Well, for example, I claim that if f is logarithmic, f of 1 must be 0. Why is that? Well, notice that 1 can be written as 1 times 1. And since f of 1 times 1 is f of 1 plus f of 1, we have what? That f of 1 is equal to f of 1 plus f of 1. Therefore, twice f of 1 is f of 1. And therefore, by algebraic manipulation, f of 1 is 0. Which, by the way, does check out with the usual logarithm. The logarithm of 1 to any base b is 0. Secondly, if f of 1 over x is defined, you see, in other words, I'm not sure whether 1 over x is in the domain of f just because x is, but suppose 1 over x is in the domain of f. Then f of 1 over x is equal to minus f of x. In other words, f of a number is minus f of the reciprocal of that number. Again, a familiar logarithmic property. Why does it follow from our basic definition? Well, notice that we already know that f of 1 is 0. We also know that 1 is equal to x times 1 over x, provided x is not 0. By the way, if x were 0, 1 over 0 wouldn't be defined, so we wouldn't be worrying about that anyway. But notice now we have what? If x is not 0, f of x times 1 over x is 0, but by the logarithmic property, that's also f of x plus f of 1 over x. Since these two together add up to 0, f of 1 over x must just be minus f of x. And we'll just take a few more properties like this, just to make sure that you see what properties logarithmic functions have. Remember again the ordinary logarithm? The logarithm of a quotient was the difference of the logarithms. Again, f of x over y is equal to f of x minus f of y. Why is that the case? Well, look at f of x over y. That says f of x times 1 over y. But again, by logarithmic properties, f of a product is the sum of the f's. Therefore, f of x times 1 over y is f of x plus f of 1 over y. But we just saw that f of 1 over y is minus f of y. So we have this familiar result now. And finally, by mathematical induction, if n is any positive integer, f of x to the nth power is just n times f of x. And the proof is rather clear. namely f of x to the nth power, when n is a positive integer, means f of x times x times x times x n times. And since the logarithmic property says that f of a product is the sum of the f's, that's equal to f of x plus etc. plus f of x n times, and that precisely is just n times f of x. In other words, notice that our definition of a logarithmic function, simply that f of x1 times x2 is equal to f of x1 plus f of x2, allows us to deduce all of the familiar properties that were known to us in terms of the traditional meaning of logarithm. And now we come to the most important question of today's lecture, and that is, what does all of this discussion have